Welcome to the videos on creating large diameter contact lenses using the wave contact lens system. We're going to start off by actually designing a contact lens, a large diameter or sometimes referred to as semi-scleral contact lens on a regular looking cornea. We're going to do that in great detail, and then we're going to step back and break down the process. I'm going to show you actually an 8-step design process which will really make designing these lenses very simple for you. And then we're going to look at some of these contact lenses that I personally have designed for my patients well over a year and a half, 2 years ago at this point. And you're going to see that the designs all follow the same principles. Well, this was a long time ago before I came up with these simple steps. They all still follow right along, and you're going to see it holds true for whether it's keratoconus, post-LASIK, or a regular multifocal style design. When you're doing a large diameter wave contact lens, following the same steps will give you great results. And the goal is really to simplify the process. Large diameter contact lenses are extremely comfortable and they have a great place in your practice. So watch these videos, learn how to make them, try them out on some patients. I advise you select your patients wisely, especially at first. The biggest challenge probably is teaching patients how to handle these lenses. Beyond that, they are absolutely wonderful. So enjoy the videos and good luck with your lenses. For this example, we're going to look at a simple spherical cornea. Nothing too funny going on here, but what you're going to notice as we go through this example, and then we'll go through some more advanced style cases, that the design principles and the simplicity of designing a large diameter contact lens using the wave system is really simple and very reliable. So first thing we want to measure is the corneal diameter. So here you'll see it's already up at about 11.19. We'll just round up to 11.2. And this, more than any other design, it's important to take note of that. So I'm just going to open up a little notepad here and jot down that our diameter is 11.2. And now we're ready to open up wave. So we'll just put focus on our window there and click the little wave button, and wave will come up. It's coming up to the side of the screen here. And once that's up, we'll get right to work. Now, the 11.2 is important because it's going to determine two main factors. The big one is the diameter of the contact lens. And my general rule of thumb is to go about 2.5 millimeters larger than the horizontal corneal diameter, the horizontal visible iris diameter, as it's called. So here we had an 11.2, so we're going to design this lens at a 13.7. And just so it's easier to view everything, I'm going to minimize that so we have a clean background. So I'll write that down too here. So we're going to do a 13.7 for the contact lens diameter. Again, I like to do about 2.5 millimeters larger. Better to err on the larger side than the smaller side, because you don't want to get too much into the limbal area. You want to get out beyond that and onto the sclera. The minimum I will do one of these is a 13.5, and the max wave will allow us to do one is a 15.0. Now there's a lot of push in the marketplace. You see a lot of these lenses coming out from laboratories. Their measurements are 15.5, 16.0. They're big lenses. With wave, I really don't see a need to go that large. If you're experimenting with these and you want to go larger, that's perfectly fine. I've just never personally found a need to go over, or I've always thought a 15.0 was plenty large. Let's put it that way. And for this case, we're going to do a 13.7 based on a smaller cornea measured at 11.2. So the next question is where we're going to place our back OZ and our IC. So remember, the OZ is simply stating how wide we want the central curvature of this lens to go before peripheral curves can pick up. Now, as compared to a corneal design, usually that back OZ, we're going to make it just a touch smaller here. And I like to keep the difference between the OZ and the IC about 2 millimeters on your average case here. So I'm just going to click down into the corneal view and pull out here. And we'll see that right around here, probably, I'm guesstimating. I usually tend to go out beyond the pupil quite a bit, and if you look down on the view here, as we come out to 5.5, That seems like the good spot. That's where it goes from lighter green to darker green on our topography. So 5.5 is probably going to be just right. And then I like to keep, as I said, the IC about 2 millimeters out beyond that. So we'll put our OZ at 5.5 and our IC at 7.5. Okay, so now we pretty much know all the values we're going to use to design this contact lens. Hard part's done. We're going to go down to Auto Design, Custom Settings, and I still have this set at the default setting. That's fine. If you do a lot of these, you might want to save a definition for a large diameter lens. So we're going to start up here, the OZ 5.5, that's what it is by default. That just happens to work out perfectly here. And on most regular corneas, these settings seem to work fine. So 5.5 and our IC is 7.5. Apical clearance, I'm going to leave at 0. We're going to adjust that later on the lens. Edge thickness, believe it or not, we want these pretty thick at the edge. Usually do about 0.27. And same with the center thickness. A thicker edge is going to help your patient to actually remove the lens and handle it, and a thicker center is going to make the lens nice and stable. If you order these too thin, they will flex. So you want a nice stable lens that the patient will be able to handle. Before we move on to some more designs or some case studies, I just wanted to make one point here which will help analyze the actual lens style and design for you. Is this pink dot. It's probably the most important factor when designing a lens. Remember, we moved it in about 0.4 millimeters smaller than the measured corneal diameter, and then we pinned it to 20 microns. So essentially what we've done, say we have the edge of our cornea, this is the limbal area right in here, that's kind of the gray side. Let's go to this side where it's a little clearer. So right here we have clearance of a little greater than 20 microns, probably about 22 microns according to this. If we go to 11.2, 22.7 microns. So we're a little nitpicky there, but in essence we have clearance over the limbal area. It's not binding down on the limbal area. So that's one very important factor with these large diameter lenses. The other thing is, beyond that, you'll notice it continues to flatten out, just like the sclera does. So by putting this point at a little bit smaller than the corneal diameter, pinning it at 20 microns, and letting the curvature just take on its own course using the Wave software, the lenses actually line up very well on the sclera. So here I'd like to walk through an 8-step design process I came up with for designing large diameter wave contact lenses. The first step is simply to record the corneal diameter. Second step is to decide on the OZ and IC placement. That's the part that may change based on the topography a bit. Number 3 is to use the auto design custom settings. We're just going to enter all those values in that we got from steps 1 and 2. Number 4, simply save it and reopen it, just so we don't lose our work. Number 5 is to adjust the pink dot. We're going to do corneal diameter minus about 0.4 millimeters. Step 6 is to increase the apical clearance. We just click down at the blue dot a few times to get some greater clearance centrally. Step 7, we create more of a tear pump in the vertical meridian. And step number 8 is simply to pin the pink dot to the 20 micron line all the way around the lens. And that's really it. If there were a step 9 on here, it would simply be to save and order the lens. Other than that, this is all there is to it. So let's walk through that on a real design here. But we're going to measure the corneal diameter. So here, 11.23. This is the left eye, by the way, so it makes sense that we're about the same there. So we have our diameter of 11.2. Now we're going to go ahead. Oops, that still has all the data from before, but we'll leave the diameter there. And we're going to open up Wave and design a brand new lens for this cornea. So we know the diameter is 11.2. About 2.5 millimeters larger. It's going to be 13.7 again. So we'll stay with that for this one. I tend to make the same diameter on both eyes unless there's a reason not to. So we know we're going to do a 13.7. And I'm guessing we're probably going to have our OZ and IC about the same as well. So I'm going to move this out of the way so it's a little cleaner for us to look at. So come out to about, in between the light green and the yellowy area. Notice right there is about 5.2. So yeah, 5.5, 5.3 is going to be the same. So we'll do the same. We'll do a 5.5 and a 7.5. A 5.5 for the OZ, 7.5 for the IC. So all I'm going to do is auto design custom settings. That was step 2, by the way. Step 3 is open up auto design custom settings and enter in all those values. So we have 5.5 and 7.5. Our edge thickness, remember these are, we're just going to bump these up here. Target lens power I'm going to leave alone. We already decided on the diameter because we measured the corneal diameter. So we changed to GSIM and just move this up to 13.7. I count that as one step because you're just entering data you already had. And then we'll hit continue. So that was step 3. When this finishes, step 4 is going to be to save it. So this is probably one of the more time-consuming steps, waiting for this to finish and then hitting the save button. But it's very valuable, and again, I highly, highly encourage you to save your work at this point, just so you don't have to do it again. So we'll hit accept there, and we'll save it. And then I just have to come back here and open it up again. Okay. So there we are, 4 out of the 8 steps done already. So step 5 is going to be adjust the bevel position. And remember I said the corneal diameter minus 0.4 millimeters. So same here, we have 11.2. So we're going to set this into about 10.8 and then just drag it up. Make sure your position stays at 10.8 because that's really where you want it. And at this point we're just getting it off the green line so we can do our central adjustments. That was step 5. Step 6 is while at 100%, adjust the apical clearance to about 10 microns. Let's see, where are we there? 9.8. That's fine with me. And then step 7 is going to be create that tear pump we were talking about. So we'll just set this to the vertical meridian, change our quadrant control to 50%, and just click up here about 5 times. And there we go. And step 8, pin the pink dot along the 20 micron line. So looks like here we just have to drag it up a bit, leaving our position at 10.8. A little bit more. Oh, maybe that was too much. I like to start at least at 1. Now I'd like to go through a few actual case studies. These are real designs made on real corneas, obviously, that have been dispensed, and the patients are very successful wearing these designs, and they have been for a year plus, at least in any of these designs here. So I've changed the patient name for obvious reasons, but I'd like to outline some of the designs here, and you can see what was done. So let's open up lens number 1 for the right eye. This obviously is a central cone. And let's take a look here, how this one may vary from some of the others. So we see here, we have our OZ and our IC are a little bit further apart than I would normally do them on a regular cornea, and the reason is we put the OZ in closer to the cone, and then the IC is out more towards when we get out to the periphery of the cornea. So let's see the OZ, notice it's right outside the cone basically, and then the IC is out towards the blue of the cornea. We go vertically, we have a little more lift than we do horizontally, and all the way around we're above the 20 micron line at this point, but we're still out there and it's pretty consistent all the way around. So that was lens number 1. If I open up lens number 2 that I needed to do for this patient, let's see what was done differently. They look pretty similar all the way throughout. Oh, we had an over-refraction. Okay. So, as you see, lens number 1 was designed using this exact principle on a cone. Lens number 2, all I had to change was the over-refraction. And for better optics here, I did a greater center thickness and kept the edge thickness pretty high as well. And here, still great center thickness and a thick edge. A thick edge on one of these designs really does not interfere with comfort. Remember, they fit more like a soft lens. So that's a design on a central cone. Done also in GSIM, by the way. Yep, let's close that. And we'll close that. And let's look at the left eye. Very similar. And lens number 1. So here I started with a 13.8. And I went up to a 14.0, so I went a little bit larger. And same kind of principle here. Notice that pattern. So here I didn't lift it up quite as much. Keep in mind I did these all a long time ago. But same kind of principle. The back OZ is placed right outside the cone. The IC is as we get out towards the blue area. The flattening of the cornea, we'll call it. Higher center thickness and edge thickness. And it looks like on lens number 2, I needed to increase the center thickness. I was bearing a little bit too closely, the apical clearance. So we started off with 6.8, and I increased it up to 13.8 to get up and over the cone. And lens number 2 worked just fine, and I had a very small over-refraction, plus a quarter. Other than that, the design looks pretty much the same. And this is another point I want you to note here. Don't worry about what's going on out here. You notice this little bump here, so this is showing us that we have all this clearance all of a sudden. Wave has no idea what data is going on out at 12.3 millimeters. I mean, we're over the cornea to begin with here. So don't worry about how this actual line looks. This is stating that we have tear clearance off the cornea. We're not even on the cornea, so ignore that. As long as you have this pink dot a little smaller than the corneal diameter and right at about the 20 micron line, you're going to be in good shape. So we'll close those, and that was a central cone. The next design style we're going to look at is a post-LASIK. This patient was uncomfortable with any corneal design and more so had glare issues. So we designed a large diameter lens. Let's open up lens 1 and 2 here. And you'll see I'm not perfect. I have to design 2 lenses a lot of the time, sometimes more, sometimes less. But bottom line is, when all is said and done, they work. So that's kind of what we're after, I think, for all of us. So we have 8.2 microns of central clearance to begin with. We bear down right before the blue dot, and you notice here we placed the OZ at 5.5 and the IC is probably 7.5 here, if it'll tell me. 8.98. Okay, so I went a little bit larger here, and the difference. Let's take a look at the cornea and see. I wanted to get out beyond this LASIK flap here. Okay, so I had the back OZ set inside this area, and then I had the IC set out beyond the LASIK flap. That was what happened there. And let's see, 14.2 in my diameter. What did we get here as far as corneal diameter? Or 11.9, so a little less than 2.5 millimeters larger. The 14.2 is obviously worked out fine because we stayed with that diameter. So what did we do different here? Vertically, we have a little bit of clearance, and embedding, we had an over-refraction again. So that just happens. Center thicknesses are high, 0.29, edge thickness 0.28, or a 0.25 and a 0.28. Axial, everything looked fine here. And I will tell you, this patient also came back. Regarding the glare, we took that on. Was we opened the back or the front optic zone as much as we could, just drag that all the way over, and that seemed to help quite a bit with the glare. He did come back also and want this multifocal add. So after the glare, and I hope all of you are kind of rolling your eyes a bit, thinking, great, you had glare, you had to address that, but then we wanted a multifocal. Yes. So this patient actually wears two lenses. He wears one for distance and one as a multifocal for work. So he can see at night and he can see at work. And the plus 125 multifocal worked very well. I wouldn't go too high with a reading add on these, but you can do a small reading add and experiment with it. Another factor we had here were very large pupils, glare, post-LASIK. Not the easiest multifocal case, but this lens worked great for a working lens. Okay, so let's close that. And let's take a look at the left eye. And we'll open up lens 1 and 2. And same here, 14.2. I did a plus 150 add on lens number 2. A little bit of clearance here, a little bit of clearance there. Centrally only 4.4 microns of clearance. And remember what I was saying before, if it's 8 microns, 10 microns, 12 microns, central clearance, it's not going to affect the lens all that much. What we're after is getting off the limbal area and allowing wave to make a flat curve which goes out onto the sclera. Other than that, everything is really fine. And we're not really concerned with the center of the lens, the back curvature view matching the corneal view as much as we would be. And I should kind of have a similar look to it like we have here, but it's not going to match exactly. It's not designed to do that. Notice we're pinned at the 20 micron line all the way around. Lens number 2, we got to stay there, which means it worked. Just had a little bit of an add power put in there, and that's that. So as you see, exact same design principles that we use on any other lens or any other type of cornea for these large diameters on this cornea, and they work. So that was a post-LASIK design. Okay, the next one we're going to look at is, this is a smaller cornea. It's a hyperopic prescription. Actually, it's an amblyopic eye. So we really just needed something to balance, and actually the patient can never really see comfortably through a soft toric lens. There is cylinder here. I just didn't put it in here because I knew we were designing an RSIM center. So when I designed them, I really want this spherical power. That's the main one that matters. And we only had one lens here, so this one did work right off of the bat. And it's a little bit smaller, 13.5. This cornea measures pretty small. Your caliper at 11.06. So 13.5 would be about right. Remember, if you're going to make a large diameter lens intended to rest out on the sclera, the minimum diameter you probably want to do is a 13.5. So here we have it. And the design looks pretty standard here. We have our OZ set at 5.7 and our IC set at 8, so it's still about 2 millimeters apart. If this was at 5.5 and that was 7.5, I don't think it would make or break the lens by any means. I guess vertically we have a little bit of clearance there, so we can get a little flex into this lens, get a little tear pump. We have a little bit of clearance, 5 microns centrally. And notice this pink dot stays right around that 20 micron line all the way around. And the more I've designed these, I have come to conclude that if I could pin this right on the 20 micron line, it just makes troubleshooting down the road, if necessary, a lot easier. And we have a thick edge, 0.7, and center thickness, because it's a +6 lens, is going to be pretty thick anyway, so that's taken care of. And one of the main reasons I pulled this out was designing a corneal lens on this topography was going to be tricky because it's very messy. It's not a good quality tear film. It's not a great quality topography. We don't have a lot of data. I would not really want to use this particular map to design a corneal aligned lens. It would work. It would probably be not as predictable, we'll say. So by doing this design here, we're getting over the cornea, and we're using wave to just set average central curvatures and rest out on the sclera, and it works. So that's that one. Let's close that. The next design we're going to look at is one that I had to do in freeform. When I can help it, I will do these in GSIM because we're getting over the cornea, and most scleras, as far as I know, are fairly symmetric, so I really don't have to get into too much of a freeform design. Now, when you have a cornea like this with an inferior cone, we really have to design a freeform lens. We can't get away with a GSIM in this case. And these actually just worked out beautifully. So I placed the OZ a little bit beyond the cone. We're kind of about 3/4 of the way past the cone. So all this is stating is I want the same curvature. Remember, this is out at, where are we here? This is out at 4.8. And if we look at the topography here, this second ring here is the 5mm ring. So we'll say it's about there. Saying I want the same curvature within this 5mm ring. Once we get beyond that 5mm ring, then create a freeform lens. But inside the 5mm is an RSIM. So I put these a little bit closer together in this case, so Wave could really pick up the periphery a little bit sooner. And if you notice, same principles though. Once we find our OZ and IC placement, same exact principles here. Horizontally, we have a little bearing there. I got a little less here, I guess about 4.3 microns of clearance. If I were doing this one today, I would probably bump that up to 10 just to be safe. And vertically, we have clearance throughout here. And you'll notice the pink dot is pinned right about that 20 micron line there, a little higher, all the way around. So what this will do is align nicely out on the sclera, give the patient great vision and excellent comfort. We have a 0.24 edge thickness, 0.34 center thickness. Again, if I were doing this one today, I'd probably leave this at about 0.27, just because it works. And the one thing about designing in freeform is these lenses aren't going to rotate all that much on the eye. So we want to be sure we put them on correctly. Now, thankfully, if you get a lens like this in freeform, you can kind of tell the different meridians by holding it. And it's more, can the patient tell? So you'll notice, you can even see in this profile view, the inferior edge of the lens is going to be steeper than the superior edge. We have a 34-31 sag versus a 37-96. I would expect a huge difference in sag value here because we're going to a 14-4 lens. But it's a matter of placing it on the eye correctly. And if you can do that and you believe the patient can do that, then you'll be in good shape here. If you can't, I'd suggest really trying to design in GSIM because those have a better shot of aligning properly. Now, optically, we have an RSIM center anyway, so these lenses really do center, and the patient will see through nice, clean RSIM optics. So let's take a look at the left eye, see if that one is similar here. Okay. Up in here, it looks like I have a little more clearance centrally. And so we have a point of bearing here. So what I did was I put the bearing more in the flat area away from the cones. Or excuse me, the cone. At one point. That's one thing with freeform too, because remember, wave needs only one spot of bearing. So notice we're bearing at this one point here and nowhere else on the eye. Now that's impossible to actually happen in real life, but it's just a matter of how wave displays. So as long as we have a little more clearance vertically, we're going to get a nice tear pump action there. And notice that pink dot. Again, this is the crucial part when designing any of these lenses. You want that smaller than the corneal diameter a little bit and just pin it up around that 20 micron line and you will have success. So that's again a freeform design. Same exact principle. Freeform just takes a little longer to get through and design and a little more care. But it's the same methodology on any of these corneas. And finally, we're going to take a look at this pretty straightforward cornea again that we did a multifocal for. Now this patient is an actor, so he wanted to be able to see clearly across the stage and be able to read the print on his script sheet, which apparently is very small. So we designed a large diameter lens here, 14-4. He also has pretty large eyes. And you'll notice the design follows the same principle here. So horizontally, just about bearing down, and vertically, we have more lift. And we're pinned at about that 20 micron line all the way around. What I tend to do on something like this is design lens number 1 as a single vision, knowing all well that he would want a multifocal, but let's get the design out of the way first. And then lens number 2, once all was set, we put in just a low add. We didn't need a lot, so this worked out well. Again, I think I said it on an earlier one, you can get away with some add power on these. You do get, just like any multifocal, some glare issues. At night, they don't move, but the multifocal still works. You can do some monovision, stick with all your regular multifocal troubleshooting techniques that you have and strategies that you use, and you can use them. I've done up to about a 2 add with a semi-scleral or large diameter lens, and it does work. They work great. They don't always work, but they do work. So here, let's see, we have the design. We got to leave just about the same, it looks like. Yep. And we just added a multifocal, a +1 add, very little. I didn't go too far in, just a little bit, and this did the trick for him. So he's been wearing this lens for, I think, about a year and a half, or this design, I will say, for about a year and a half, and has been very happy. And let's take a look at the other eye. Which looks very similar. And we'll open up lens number 1 and lens number 2. And see if we had the same luck here. Yep, so lens number 1 followed the same principle, a little central clearance, vertically a little more lift, and we get this pink dot right around that 20 micron line, a little smaller than corneal diameter. And lens number 2, looks like we had no design changes, just the multifocal and a little over refraction. So here probably did a little modified monovision. And remember, keep the edge thickness and center thickness up higher than you normally would tend to. If I were doing these again today, I would probably up these a little bit more just for better stability. Other than that, that is all there is to that. So you've just seen how to pretty simply and effectively design a large diameter contact lens using Wave software. We went through kind of an 8-step process on designing the lens, and then we looked at a bunch of different styles of topographies and saw the designs that are actually used and that those patients are currently wearing and happily wearing and have been wearing for over a year plus in all of these cases. So what I want you to take away from this is, one, the design process is fairly simple. Once you do a couple, you kind of memorize what you're doing and it becomes really easy. The most important piece is that pink dot, a little smaller than the corneal diameter, and punch it up right at that 20 micron line all the way around the lens at 360 degrees. And you're okay to get off the cornea centrally because there's no point in bearing down on it, and you want to have a little bit of a tear flow through there. So we don't make it a perfectly smooth back surface intentionally. And that's really all there is to it. So I encourage you to test these out, try some on patients you know will be good candidates for these large diameter lenses. Have fun with them, and you'll find that when you get the hang of these, it's just another tool in your contact lens toolbox, and you're going to make some patients very, very happy. So I hope you enjoyed the videos, and thank you for watching.